All right. So the proof of this statement, the key to understand this statement is actually very elementary. It's the Cauchy inequality that we all know since high school or elementary school. And now we will just apply it in a slightly unusual context. So the Cauchy inequality applies also to quantum field theory. We just don't normally use it. But the way it applies to quantum field theory is the following, that let's just take a 4-point correlation function in some geometry, which is not where the operators, so the geometry itself, so the situation is not symmetric, right? Here, clearly, the non-symmetry of the situation is due to the fact that the cylinder itself is symmetric, but the operators are inserted in a non-symmetric way with respect to this line. And so the way we say is that this correlation function is not reflection positive, and so it's not going to be, this situation is not reflection positive, so this correlation function is not going to be positive in general. So we take an absolute value of this correlation function, and now we do the cut and glue argument. We say that we can cut this cylinder along this line, and we can reglue. We can reglue it by symmetrically reflecting these 2 points. So here you see I reglued it phi1, phi2, and here symmetrically phi1, phi2. And same thing here, I again reglued it, phi3, phi4, phi3, phi4. And then the claim is that this is going to be less than square root of the product of this. And here, the correlation function is in the reflection positive situation. So this is positive, the whole thing is positive, and is bigger than this. So of course, why am I allowed to do this? Well, it's because this correlation function, I can understand it as the scalar product of 2 states. So inserting 2 operators phi1, phi2, I'm creating a state on the sphere, an in state, and phi3, phi4 corresponds to an out state on the same sphere. And this correlation function is just the scalar product of these 2 states, of these 2 states. And the scalar product of 2 states is less than the square root of the product of the norms. That's it. And the norms correspond to these 2 correlation functions. So this is a very trivial fact, and you can use this in any geometry. You can use it in flat space, you can use it on the cylinder, you can use it on a sphere. Actually, you can take any geometry, cut it in 2, and then reglue it, and you will still have this inequality. So it's just a general fact of quantum field theory. And so this inequality, it's true for the full 4-point function, but also it's true for the tail in the OPE series. So what I mean by that is that here I got the 4-point function as this infinite series. But now let us take this infinite series and consider a tail on it. By tail, I mean the sum of all terms with n bigger than a certain big number. Now, you see that in that tail, and now I'm going to write the same thing for the other objects here, for these 2 guys. But these 2 guys are going to involve exactly the same exactly the same matrix elements, except that here I will have phi1, phi2 times phi1, phi2, or phi3, phi4 times phi3, phi4. So I can actually do the normal, Hilbert space Cauchy inequality applied term by term, the normal algebraic Cauchy inequality applied term by term, and I'm going to get that this inequality actually applies for the tails. So what this means is that if I want to study the convergence of the series which represents this 4-point function, I can equally study the convergence of these 2 series, and then if these 2 are convergent, that this one is going to converge with the same rate or faster. So why is this interesting? Because the reflection positive 4-point functions they have a series which has all terms positive, explicitly positive in them. So we are, so you remember that I said that one issue that we would like to understand if the convergence has to do something with the cancellation between positive and negative terms. And since I can apply this Cauchy inequality argument, this shows clearly that the convergence has nothing to do with cancellation. So here I have a similar 4-point function, which is given by a sum of positive terms. So either they converge or they diverge. There's no tertium non datum. So there's no possibility for cancellation.
C's are real, or you should use the modulus of a C?
Yeah, it should be C times C dagger.
Okay.
Yeah, so here the real C's. Yeah, so the C times, it's clear that I'm considering here the complex conjugates. Yeah, sorry, it should be C dagger, C dagger. The fact that there is no room for cancellation allows us to show that this series not only converges, it converges actually exponentially fast. By this I mean the following, that if you take this series and if you take the tail, when you take all the states bigger than a certain E star energy, then this tail is going to decrease. So you fix tau, then you vary E star, and the size of this tail is going to decrease like e to the minus E star times tau. So this is this decoupling theorem which I was referring to. The contributions of high states are exponentially suppressed, and this fact is valid independently of the size of this coefficient Cn. Or better say, of course, for this fact to be valid, the UPE coefficient Cn cannot be large. But actually, in any conformal field theory, in absolute generality, they cannot be large. So here is the proof. So you see, I'm going to give a rough proof of this theorem. So the only way, so every term in this series, of course, has an exponential suppression. So the only way this cannot fail, this can fail if this coefficient Cn grow with n. And actually, they have to grow pretty fast. They have to grow exponentially fast.
Sorry, but I would, like in string theory, you could have something like Hagedorn, a phenomenon that is the number of n you are entering. You have with increasing of E is increasing very fast. So
the number, but
primaries.
No, but I explained that there is a Hagedorn phenomenon. The number of primaries increases very fast, but their OPE coefficients, I mean, if you take Cn, you see, strictly speaking, I have to argue here in terms of density. So I have to define the density. Cn times the number of primaries with the given energy. So in order for this to fail, the density of states weighted by the OPE coefficient has to grow exponentially fast. But this is impossible, because if it grows exponentially fast, then this series is going to diverge at finite tau. At some finite tau, it's going to diverge. But it cannot diverge at any finite tau, because at any tau, this series actually describes for us this 4-point function, which is a finite object in conformal field theory. And moreover, we know that this object, the only way it can become large is if tau goes to 0, and then this limit is described by the OPE. So the asymptotics of this object in the limit tau goes to 0, it's given by the OPE of these 2 points colliding. So you can try to do it more precise, and this has been done more precise. But the end result is that this series converges exponentially fast. And you see that for this last step, to say that since this 4-point function is finite, Cn's cannot grow too fast, I use the fact that there are no cancellations possible in this 4-point function. So that's why it's important to run the Cauchy argument first. So So this 4-point function is going to be convergent in any geometry, this OP decomposition. And in order to impose the conformal bootstrap equation, we of course have to consider all possible geometries, like we have to vary U and V. We have to impose the conformal bootstrap equations for all U and V. And you know, you could say that, okay, if I'm considering the geometry where this distance is much larger than this distance, then you could say that, well, it's kind of obvious that the OP decomposition behaves well in this limit, and in the opposite limit, it's going to behave well if I use OP for these two operators. But the geometry that we really need to impose conformal bootstrap condition is not this or this. The geometry that we need is this, is the geometry where I insert two operators at the vertices of a square. And the reason is clear, because the conformal bootstrap equation says that the S channel should be equal to the T channel. So in order to impose this constraint, we have to find a geometry which does not privilege one of the channels over the other. So we have to find a channel, we have to find a democratic geometry, and this geometry is clearly democratic. So the idea is going to be to take this geometry and, of course, perturbations around it, small perturbations around it, and analyze conformal bootstrap in this, for all these perturbations. So you can ask, well, I gave you a general argument that the conformal block decomposition converges, but how fast does it converge for this geometry? You know, this geometry, okay, you have to just compute, and then you will find that it will converge or rapidly or fast, but you have to make a computation. And how do you do this computation? Well, in order to do the computation, you have to map these points on the cylinder. And since the convergence rate depends on the distance, so my argument that I gave you for the convergence rate depends on the distance, you have to aim for the mapping in which this distance is the largest. So, of course, you see, yeah, so you have to map for such, you have to aim for such mapping. And so you have to go through two steps. First, you take this geometry, and then, of course, you can use a conformal transformation to use the 4 points anywhere you want. And it turns out that in order to, as a preparatory step for this mapping, you map them on a line. So all 4 points on a line and in a symmetric position. And the distance between the points, the relative distance, is going to be fixed in terms of, in such a way that the cross ratios corresponding to this configuration are the same as for this configuration. So you find this conformal transformation, then you map here, and what you find is that the parameter e to the minus tau, which controls the convergence rate for the OP decomposition of this geometry, is given by 3 times 2 square root 2, which is actually a pretty small number. It's 0.17. So if you consider the OP decomposition in this geometry, then the contributions of high primaries are going to be suppressed by 0.17 to the power delta, which you wouldn't expect a priori, because it looks like this geometry has really no small parameter in it built in. It's just all distances are order 1. So it could be, I mean, a priori you could say that, well, maybe here I will find something like 0.5 or 0.6. So some number which makes the series convergent, but much more slowly convergent. Well, nevertheless, it turns out that it's 0.17. So this is nice. It's just a fact of life. Excuse me?
This number, you just says, well, 3, you will change the conclusion. Does it depend on the size of the group of the CN coefficients?
No, it was precisely the point that, you see, so I claimed that the OP coefficients in the conformal field theory should conspire in any conformal field theory in such a way that, that the density of states multiplied by the OP coefficients grows with a certain rate which is only determined by the dimension of the field, of the external field, right? of the field phi on which you started. So that was the claim. Now, once you fix the density of states, once you fix this density of states times the OP coefficients, so this just determines the total normalization in this formula, which is an order 1 thing. It does not depend on the CFT. But still, you are still interested to know what is, so the coefficient in this formula is universal. That's what I want to claim. It does not depend on the CFT. It's just a constant. But still, for any given geometry, there's going to be tau that tells you how well it converges for this particular geometry. So since the geometry we are interested in is the square geometry, you go and compute what is tau for the square geometry, and you find that it's 0.17. E to the minus tau is 0.17. So it means that for any CFT in the square geometry, the convergence of the OP decomposition is going to be a universal number of order 1 times 0.17 to the cutoff level. And you can check this fact, by the way. You take your favorite conformal field theory, like the two-dimensional Ising model, you compute what the OP coefficients are, and then you can check that indeed they conspire to make sure that this is true. So, so by now, what we discussed is that all this part concerning the convergence of the conformal bootstrap equation, it was served to convince you that it is, of course, the problem is more difficult than in 2 dimensions because you do deal with infinite series as opposed to finite series, but it's not hopeless because the series with which you are dealing are convergent series, are convergent fast series. And so you can hope to really extract some information from those series. The problem is still how, right? So that is the problem. And so I'm going to explain how you can actually go about doing it in practice. So let us go back to the 3-dimensional Ising model. So any questions, by the way? No. So this is a recap. So we consider in the 3-dimensional Ising model the 4-point function of the spin field, and it's going to be of this form, where the function GUV is going to be 1 plus the sum of conformal blocks with positive coefficients. And we know that this function GUV satisfies this constraint, which comes from Cauchy symmetry. And we know that in this right-hand side, all fields which appear in the OP sigma times sigma their conformal block will appear. So all these fields will appear, and infinitely many other fields will appear. And a priori, all fields above unitarity bound should be allowed to appear. So we don't want to, so what we are going to do is not going to be like, well, let's just guess the spectrum of the 3-dimensional Ising model. Suppose that it's just integer valued fields, or all fields proportional to square root 2, and so on. And let's just try to solve the bootstrap. We are not going to do that. That's clearly not, there's no evidence for this in the data. So we have to be we don't have to, we have to be inclusive. So we have to allow all these fields in principle to appear, and the theory will tell us which ones do appear and which ones do not appear. So, but one thing which we do know, of course, is the unitarity bound. So we know that for spin L, for spin 0, we are only allowed fields above 1/2, for spin 2 above 3, for spin 4 above 4. And we actually do know that for spin 3, this bound is going to be saturated, so there is a T mu nu, will be there. While for spin 4, we know that it's not going to be saturated. The first guy is going to be slightly above. And also for spin 0, it's not going to be saturated. The guy epsilon is quite a bit above the unitarity bound. But before I tell you what kind of trick we can play, I should tell you a little bit about these conformal blocks. So I introduced already these conformal blocks, which are the functions which enter the OP the conformal block decomposition, and I told you that these functions are in principle known functions, completely fixed by conformal symmetry, and it turns out that if you want to play this game, which I'm going to describe, you really have to know these functions pretty well. So you have to really control these functions. And there was a lot of work on that. And so we have the theory, there is a big body of results about these functions, although the theory is not yet in the shape, is not yet in the totally ideal shape. So let me explain. So it turns out that these conformal blocks are simple, relatively simple functions if the space-time dimension is even. So if the dimension is equal to 4, 6, even 2, then these conformal blocks, they are basically products of hypergeometric functions. So for example, in 4 dimensions, so I was telling you that the conformal blocks depend on U and V, but it turns out that in order to get simple results, you have to introduce this coordinate Z. Now, you would be surprised that I am introducing the complex coordinate Z in, of course, in 2 dimensions. We do it all the time, but in 4 dimensions, it may sound a bit counterintuitive, but actually, you can introduce also the Z in 4 dimensions, and the way you do it is the following. So so as I told you, we can fix 3 points wherever we want. So we choose to fix 1 point at the origin, 1 point at the distance 1, and send 1 point to infinity. And then you are still left with 1 point free. But you see that this geometry 0, 1, infinity, it has a rotation symmetry around this axis, around the x1, x3 axis. Because infinity, there's only one infinity, it's compactified. So you can rotate by bringing this point x2 to one plane, to the plane of this screen. And then the complex coordinate of this plane is the z. And then it turns out that in this variable, the conformal blocks drastically simplify. So this was a discovery of Francis Dolan and Hugh Osborne in 2001. So they realized that in 2 dimensions, if you use these coordinates, then the conformal blocks are simply, they completely factorize, so some functions of z times functions of z bar. And in 4 dimensions, you see that they don't factorize. They factorize up to this rational function of z and z bar. Now, this is just a miracle, if you wish. Something similar happens also in 6 dimensions. So I should stress that in 2 dimensions, if you do 2-dimensional conformal field theory, there are 2 types of conformal blocks that you can introduce. You can introduce the small blocks and big blocks. The small blocks are going to be the sums over global SL2C descendants. And those are the analogs of the blocks that I'm discussing here. So these are going to be given by products of hypergeometrics. And then there are long blocks where you sum over all Virasoro descendants. Those are, of course, much more complicated, and they depend on the center of charge in particular, while these small blocks do not depend on the center of charge. So that's clear. So this is the situation in the even dimensions. Unfortunately, we want to solve the three-dimensional conformal field theory, so we have to go to odd dimensions. And in odd dimensions, conformal blocks are quite a bit more complicated. So such formulas are not known. And the reason why they're more complicated is that these conformal blocks, as I'm going to show next, they can be thought of as some solutions of eigenfunction equations reflecting the invariance under the conformal group. And it's a well-known fact that this kind of eigenvalue equations, kind of orthogonal polynomial type equations, their properties of their solutions, they depend very much whether you are in even or odd dimensions. So it's just like with the Huygens principle, you have, in 4 dimensions you do have Huygens principle, in 3 dimensions you don't. So it's the same thing which somehow is happening here. So in 3 dimensions it's more complicated, but still there is a body of results which you can use. For example, in the scalar conformal block in 3 dimensions, in d dimensions, this is given by some kind of power series in u and v, 1 minus v, with known coefficients. But it's a double power series. You see here, we are reduced to hypergeometric is also a power series, but it's a single power series. While here we have to deal with this mixed double power series. And this is just the scalar block. And then if you want to go to higher spins, then you have to use some recursion relations, which are also due to Dolan and Osborne. But you can do it. And the nice thing is that since we know that the higher dimensions are going to decouple, and since we know that the higher spins, due to unitarity bounds, means higher dimensions, you only have to, for example, if you use recursion relations, you only have to use it for finitely many spins, and then things decouple. So another thing that you notice by looking at this formula is that it's what I said. The dimension, the space-time dimension here enters just as an analytic parameter. So these conformal blocks, they are in dimension equal to 3. They are just as complicated as in any fractional number of dimensions. So if you want to use conformal bootstrap in 3.99 dimensions, you just start from this expression with different d, and then you do the whole thing. So this is what I said. Actually, the best way to obtain these conformal blocks is to observe that they satisfy a second-order partial differential equation. And so the operator here in this partial differential equation is the Casimir operator of the conformal group. Now, let me explain a bit more in detail how it works. So, of course, the Casimir, so we know what the Casimir is, so it's just the product of all generators. But here we have a 4-point function, and here we have a partial wave of the 4-point function, which is just 2 3-point functions put together, or 2 p's put together. Now, let's take this 4-point function. Maybe I should use the blackboard. So the conformal block is defined by using the OPE. Well, let me denote it schematically like this, and then fusing it with another OPE on the other side. Right, so this is going to be the conformal partial wave. Now, let us take here some conformal group generator. Let me denote it G. And this conformal group generator, I'm going to denote it G1 to remind me that it acts at the point 1. And here I'm going to consider another generator, which I will call G2, which will act at the point 2. So I'm considering my partial wave, and I act on it with G1 plus G2 times conformal partial wave. Here I have an intermediate point, x4. No, not x4. Let me call it y. Right? The OP is conformally invariant. It means that I can replace G1 plus G2 by minus the generator which acts at the point y. And this is the same argument by which I argued that the conformal partial wave satisfies the same word identity as the 4-point function itself. But now let me do it twice. So I'm now going to, again, apply G1 plus G2, and again push it to get a generator which acts at the point y. So I get here gy squared. So this whole thing is going to give me gy squared, acting on the operator inserted at the point y. But now let me do the sum over all generators. So I'm going to get here a sum over all generators G is going to give me a sum over all generators G. Well, this is the Casimir, right? So this is the Casimir, which when it acts on the operator y, on the operator that I'm exchanging, and this was the operator of dimension delta and spin L, the Casimir, the eigenvalue of the Casimir acting on the operator delta L is known, and it's this one. So it depends on spin quantum number and on the dimension quantum number. So this is why the conformal block satisfies the eigenvalue equation. But on the other hand, I should remember that these operators G1 and G2 acting on the primaries, these are just first-order partial differential operators. And I have to apply them twice. So I'm going to get a second-order partial differential operator, whose form I just have to compute. It's a computation that you do once and for all, so it's a known operator. It just depends on the number of space-time dimensions and nothing else.
In two-dimension, can you write the two-dimensional form of the Casimir? Just to have an idea.
You mean you want me to tell you what it's going to be, or just to give an example?
Two questions.
Yeah.
What happens to that equation in two dimensions? Does it become something which is familiar?
Well, it becomes a hypergeometric. First of all, in 2 dimensions, since the conformal group completely splits into 2 parts, the Casimir is going to split. So you will get a Z Casimir and a Z bar Casimir. You compute this, you have to sum over all generators. For example, for K, you have to substitute delta Z ddz plus Z square delta Z plus Z times dz, and so on. Then once you do the sum, you find a hypergeometric operator. So this explains why the conformal blocks are hypergeometric functions. But if you do this for the 4-dimensional case, you will find essentially the sum of hypergeometric operators, one depending on Z, one depending on Z bar, plus some term which couples Z and Z bar. But it turns out, and this was the discovery of Dolan and Osborne, that if you do this ansatz, then you can decouple Z and Z bar again. And so you find that the solution is simple. But unfortunately, this can only shift the dimension by 2. So from 4 you go to 2, and 3 is left out. So, but then there is actually another way, more simple way to think about these conformal blocks, which I even already discussed, kind of. So let me go a little bit back. So I wrote here for you the expression of the 4-point function as the sum over the intermediate states, and here I said that we have to include all the states, primaries and descendants. But now suppose we take this sum and we just pick of it a piece of this sum which corresponds to a given primary and all of its descendants, just a piece of this sum. So this piece is the conformal block of that primary expressed in these coordinates. And if you view things this way, then you realize that, first of all, you realize that the primary will always dominate, the contribution of the primary will always dominate the conformal block. Because I told you that all descendants are suppressed by a power e to the minus tau, and e to the minus tau is going to be for us 0.17. And even actually, if you are dealing with a 4-point function of identical scalars, then the suppression is going to be 0.17 squared. And the reason is that for the identical scalars, well, actually what matters is not for the identical scalars, but for the use of this symmetric configuration. X times, so the use of this symmetric configuration, x minus x, ensures that once you couple the primary, the first descendant which you're going to couple is going to be at level 2, not at level 1. Because in this symmetric point, if you take the OPE phi of x, phi of minus x, then the first term of the OPE is O of 0, and the second term is on the second order in x, just because of symmetry. And so the contribution of the primary is always going to dominate. This is the first thing. And second thing is that the contribution of the primary is very easy actually to understand what it's going to be. So so how should I put it? Here, okay, this geometry is a bit not sufficiently general. So because here I put all the 4 points on one line, but I said that I also have to consider perturbations around the square geometry. And there are going to be 2 types of perturbations. One perturbation is when I change the distance between these 2 points a little bit. And another perturbation is if I take these 2 points and I rotate them by some angle alpha around the origin. Now, if I change the distance between these 2 points, this what this does for your conformal block, it's clear. It's just instead of having e to the minus tau delta, tau changes, it just rescales the conformal block. But what happens if you rotate these 2 states by an angle alpha? Well, this is also clear. This is also clear if you think in terms of the cylinder. So you have here 2 operators phi, they create a certain state, and then they annihilate in the other pair of operators. And this state has a spin L. So now the question is, what is the dependence of the product of the matrix elements on the relative angle between this pair of points and this pair of points? So if you do particle physics, then there is an equivalent formulation of this problem. Suppose that you have 2 particles, 2 spinless particles. They collide, and they form a resonance which has spin L, like a Z boson. And then this resonance decays again into the same pair of particles. But the decay products fly out at a relative angle alpha with respect to the initial direction. So the question is, how is the amplitude for this process going to depend on the angle alpha. And the answer to this problem is, of course, elementary. So if you're in 3 dimensions, then this is going to be a Legendre polynomial. And if you are in d dimensions, this is going to be a Gegenbauer polynomial, the so-called Gegenbauer polynomial. So here we get this result that the dependence of the conformal block on u and v in these coordinates, in these very special coordinates when I insert ports symmetrically, is going to be given by a power of the distance, r to the delta, times the Gegenbauer polynomial of the relative angle cosine alpha. And this formula it gives you a very accurate approximation to the conformal block. So the corrections are of the order of few %. And also, it's extremely easy to get the correction terms in this formula as well. So you see, the reason why I'm stressing is that since we have seen that the explicit expressions for the conformal blocks could be difficult to come by, if you are interested in all terms to all orders in the descendants. But since the series, the conformal partial wave decomposition converges exponentially, it may not even be necessary to know all those terms. Suppose that you just by brute force compute the subleading coefficients, say up to level 10 or 20. I'm telling you, it's very, very simple to do this. Then for all practical purposes, this may be enough, because it's already going to give you accuracy of the order 0.17 to the power 20. Which is like, it's a pretty small number. This one, because the So I'm analyzing this, for some reason here, the echo is particularly bad. So I'm analyzing this geometry. So I'm inserting here 2 operators. I'm inserting here 2 operators here and 2 operators rotated by an angle alpha, right? And so I'm representing this 4-point function as the sum of exchanges of states of various spin. So in particular, there's going to be the primary state, delta L, and its contribution is the one written there. So it's proportional to the Gegenbauer of the cosine alpha. But the conformal block also includes contributions of descendants of this guy. So this guy, of course, is going to have the descendants. So it's going to have the descendant P mu delta L. So here we will have, so this is going to be spin L plus 1 and spin L minus 1. But these guys are not going to couple in this geometry because of the antisymmetry x minus x. But they're going to be the descendants of this form, P nu delta L. So they're going to be states of spin L plus 2, L, and L minus 2. And their contributions are going to be proportional to Gegenbauers of different spin with positive coefficients because of unitarity, but you have to compute those coefficients in order to know what the contributions are. So if I just drop completely those, then I get error of the order of few %. Other questions? So actually, I think I'm going to stop here because we are you know, what I did, I basically explained to you all the tools that we have at our disposal. And now, then the next lecture, the final lecture, is going to be how to put these tools to use and extract concrete results, concrete predictions for, say, the three-dimensional Ising model operator dimensions. So what does conformal bootstrap tell us about the dimensions of the operators in the three-dimensional Ising model? So I'm going to stop here for today.
Are there any questions?
Suppose you play this game in a large N theory.
Yeah.
Where do you get some simplifications? I mean, this, the equation you have written are valid for any number
Yeah.
of degrees of freedom.
Yeah, sure. You get a simplification. Unfortunately, it's the simplification of not precisely of the kind that you would like, in the sense that what you get is that in the large N limit, the equation is trivially satisfied. Because in the large N limit, the OPE of two scalar fields, say, phi, is dominated, well, let's take unequal 4, like everybody's familiar. If you take the OPE of two, say, chiral primaries, then it's going to be dominated by the single trace, by the double trace operator, which is the multi-particle state, which will have dimension exactly twice the dimension of the chiral primary. And if you sum up all those terms, and there are going to be infinitely many of them, then what you will get is just the 4-point function of the primary in the large N limit is just given by disconnected diagrams in the ADS bulk. You will just be reproducing, you will be just doing a lot of work to reproduce the two propagators. So the interesting part would come with the connected diagrams. But it has been shown that also in that case no miracle occurs, in the sense that those 1/n corrections to this connected 1/n corrections, they are in one-to-one correspondence of just writing down some operator in ADS, some local operator in ADS, and using the usual rules of ADS CFT to compute everything. So if you work to the first subleading order in 1/n in Bootstrap, this was shown in a paper by Penedones, Polchinski, Sully, and somebody else. Unfortunately, I don't remember. You don't gain anything over just doing ADS CFT. So that's why I believe that if you want to if you want to leverage the power of this conformal bootstrap, you should probably go in the direction of maximal distance from the large N. There the advantages of this approach are going to be most kind of evident.
How do we know that the Ising model is a reflection symmetric, positive reflection symmetric?
So you have to check this on the lattice, right? Do we agree that if we check if on the lattice it works, then it's also going to work on the continuum limit? Okay, so in order to check this on the lattice, so on the lattice we take, this is our lattice, and then we insert, say, okay, this is going to be our separation plane, and then we insert, say, one operator here, one operator there, which is a reflection positive situation. So we write down the correlation function SI, SRI, e to the minus, and here I'm going to write down the the Ising action, so the Ising partition function, the Ising action, the Ising Hamiltonian, so it's just sum over Sij, Si, Sj, Ij, 1 over T. Now, what you notice is that this action, let's write it H, it trivially splits into two parts. One which is the observable, one is the spins which sit in the upper part of the plane. Plus yeah, there is some problem here. I thought I knew the answer to this question, but I'm pretty sure I can reconstruct. But maybe let's do it offline.
But there might be interesting systems in quantum matter which are not critical systems.
Yes, that's true. That's true. There are some interesting CFTs. Yeah, there are some in statistical mechanics. There are lots of systems which are not unitary. So one would have to understand also how to do Bootstrap for them. But this I'm pretty sure because it's in the books on. CPT. Well. No, but the question is, so if you look at a particular lattice action, you should be able to check if that action is reflection positive or not. Like if this is a local action, you should be able to see clearly that this kind of correlation function is just positive. But and this has even done in these books of constructive quantum field theory. While for other actions which are defined, for example, in terms of loops and so on, which people consider sometimes in statistical mechanics, you will see that there is no clear way to prove this reflection positivity. And actually, they are not reflection positive. But this, I have a bit blocking point. But let's discuss it offline.
Okay. All right. Well, with that, I'll just remind you of the 2 sign-up sheets here, one for Lavatee, one for vegetarians. And let's thank Summer again for a lot of work.